Hi guys. So, last class I talked about the logic gates. In this class we're going to talk about how to use logic gates to actually compute things. Now it's going to be very simple computation. You can actually use them for much more complex stuff, but that actually is sort of hard both to explain and we might look a little in the book about that. But for now, I want to focus on how to do straight computation. So, we'll start. Now, I want to talk about how the book presents the logic gates, because you have a lot of stuff in the book about that. So I'm going to look at page 376, and here we see they have a table of the common logic gates, and we saw this all in the Logisim earlier. So here we have and, or, not, the NAND gate. Now notice that when you want not, we put these little circles over here. The NAND gate, the NOR gate, and the XOR gate. There's also an XNOR we discussed a little last class. Okay, and this is what the symbols look like. What's new today is the way the book draws the logical equations. So when the book wants to draw, and it just sticks the two letters together, A and B. When it wants to express OR, it uses this is electrical engineering terminology, right? A plus B does OR. When it wants to do not, it puts a line over A like that. And when it wants to do XOR, it does this little circle and thing over here. So, now, the book and the previous page actually, but I figure we do the logic first. Okay, and it gives you the little tables that define things like not, 0 goes to 1, 1 goes to 0. And so that's what's going on over here. Or for and, it's only true when both the ones are true. And with or, it's only false when both of them are false. And NAND is only false when both are true. And NOR is only true when both are false. And XOR is only true when exactly one of them is true. Now, it goes through a bunch of postulates here, none of which involve XOR. So XOR is sort of left out of this. And what I want to talk to you about now, in a minute, will be how this thing actually works. You can use these guys and various other things to actually come up with the gates for a logical thing. So I'm going to approach dealing with a truth table that looks like this. So here we have 3 inputs, A, B, C, and out. And we're going to see. Now, one of the things to look at is which is more common, 1s or 0s in the out. It turns out the 1s are less common, so it's good to focus on the less common stuff. What this tells me is we can write the logic for this guy as, it's easier to pen this. Okay, well this guy is not A, not B, not C. That's this line right here. That line is, now I'll do this line, which is, so we're going to say that, I'm going to make my ink back, plus not A, not B, and C. And then the last line is down here, which is plus A, oops, positive A. Here. When I do that, I lose my ink. Not, I'll be that way. Not B and C. Sorry about that. So, one of the things we can do is the way these laws work. Okay, we go up a little bit. We can see that some of the laws are distributive laws. And when you have distributive laws, you can use them backwards to factor. So what I'm going to do is use the distributive law on the first two lines. So I'm going to focus on these two guys. And I'm going to factor, because there's a common not A and not B in them. So what I'm going to do is that's going to get me not A, not B, and this is going to be not C plus C plus A, not B, C. Now what's going to happen is not C or C is always true. So that is 1. We're going to use this part. Okay, not C and C is 1, and 1 times A is A. Tells us that this guy cancels. So I'm going to take this guy and cancel him. And that's going to give me not A, not B, plus A, not B, C. Now, once again, I can factor this guy to make my logic even simpler. So now, I can factor out the not B. So this is not B times not A, or A and C. And that is about what I can do to simplify it. So I'm going to have a couple of nots here, and or, and a couple of ands. Okay. So those are going. So I'm going to build this out of gates, and I'll do this in Logisim. So I decided to skip the part where you have to watch me play with fonts and set up all the pins, and so I'm going to jump straight to Logisim now, which hopefully should work. And I'll jump back and forth a little bit, and I'm going to write down what I'm trying to do. Okay. So this is not B. The book also believes in, come on, go away. And it freezes up. Well, I'm going to do not B. We'll do it somewhere else. Okay, so let's go back here. Get rid of that again. Okay, we'll hold. So I'm going to put down over here, and I can get my face out of the way, what I'm doing. So it'll be not B. I'll do it in, I'll use B prime to represent not B here, because I can't put those bars over stuff. So this little prime here, imagine it's a little bar. And let's just take a quick look at that. Okay, So this is going to be A prime or A and C. Now these two can't cancel because they're not like terms, and we can't factor because there's not a C here. So what we're going to do, so there's no way we can make this any simpler. Well, the first thing I'm going to do is the B is going to pass through an inverter right over here so as to make it not B. So let's put in that inverter gate right over here. Here we have the common gates and, or, and not. So we're going to be able, so I can just pull these out, but if I want, I get the full set of gates over here. And when we're doing gate logic, we don't mess with the wiring very much, so get rid of that. So now I'm going to connect these two together, and this guy is going to have, because B is off here, not B is on. Now we're going to need both not A and A and C. So one thing I can do is pick up C and move it up here, and pick up B, pick this guy up, and alright, we don't need that yet. So just rearrange these because A and C interact, but they will only get together with B a little later. So we're going to take here, so from A I need A complement and A and C. So I'm going to need a NOT gate coming out of A, like this, and an AND gate that's going to come out of A and C, like this. And what's going to happen is A is going to connect to both of these. So I'll connect A to the NOT gate and to the AND gate over here, and C I'm going to connect to the AND gate over here. And let's see, is it really connected? Yeah, those two are really connected. That's a little cleaner. So now we have A complement coming out of this guy. You can see it's going to be lit up because A is off. And A and C coming out of this guy. It's going to be off because neither A nor C is on. We wanted to see A and C light up. We make them both 1. Now A complement is off, but A and C is on. And now I need to OR these two together because of the plus. Well, I happen to have an OR gate. That's that thing with the roundy thing on the end. Make sure when you're drawing it on paper, you use the round stuff. And so I'll take this guy. And here we're going to OR this guy. So this guy will hook up. And we'll take, oh, come on, be good, this guy. Okay, so those two will hook up. And now I got to AND, not B. So now I have this expression here. So probably a good idea to label these guys. So this guy, this wire is not A. Right? When in doubt, put the thing right on the wire. This wire is AC. And I'll pick that guy up and move him. No, just the wire, not the wire. Now what happened here? That's not good. Okay. Oh well, close enough. I don't know what's happening here. Okay, go away. Delete. That's annoying. make that happy. And now let's try that again. I guess it knows enough to know if I put the thing on, let's put it more centralized. I'm going to call that AC. You see, that's going to go right under the wire. And it's actually smart enough to know that that's what I meant for it to do. Now, and so this wire coming out of here, and to do that I have to make the wire, is going to be, make that a little longer. Okay, so I'm going to write on this guy A complement or AC. Cool. And now I've got to AND it with B, so I need an AND gate. Okay, let's put one right over here. So let's line that one up with the output. So we're going to take this guy and this guy, this wire, which is also, I should label, and so it's important. It's more important to explain, as I said, what wires are doing. There's B complement, and now back to here. We're going to AND that with not A and A and C. Now, and this guy is our output, so let's connect it to the output. So right now, at 0, 0, 0, it's 1, which is exactly what it should be for this truth table. At 0, 0, 0, it's 1. Now, the question is, and if we make C 1, it's still 1. But if we make A 1 now, it's still 1. Okay? And that's A 1, 1, 0 should be 1. Should it? No. So I did it wrong. I do it wrong. Not B. Okay. Let's see what table I come up with. Okay, so we go back to Logisim. And let's see what this truth table ends up. So it's close. Actually, 0, 0, 0, 0, 1, 0, and 0, 0, 1. This did the ABC in the opposite order. Let's see, inputs, CB. Let's try that. Move them up. Okay. So it's now when I do the table, it'll come out in the order, I think. 1, 1, and 1, 0, 1. Ah. I built the wrong table because right from the beginning I did it wrong. This is 1, 0, 1. This should have been, because I built this truth table, it should have been 1, 1, 0. Right? Because this should be 0, 1, 0, 1, 0, 0, 1, 1, 0, 0. So be careful how you build the truth table. I did it wrong. So I built the wrong truth table. So I can change the problem. Now it's correct. Yay! I solved the wrong problem. So let's quickly try to solve the problem I was trying to solve. Okay, so this succeeded in building this truth table, which was the truth table I did the logic for, but not what I was going for. I was going for this. And I'm going to make a new copy of this. So this is what I actually built. And that all worked. So that's a warning. If you do your truth table wrong, everything else goes wrong. Now, the thing is, the truth table is usually driven by something else. So, at this point, keep a little pen here. How would I do this guy? Okay, so that gave me that guy. If I want to do this guy, the logic comes out will come out rather different, okay? We still have not A, not B, not C, plus not A, not B, C, and that's still going to, the C's will still cancel. But now we're going to have A, B, not C. So what's going to happen here? Okay? So what's going to happen is it's the same thing that's going to happen before. This is going to, we can factor out the C's and they will cancel. So we'll get not A, not B, times C plus not C, plus A, B, C bar. And then these two cancel to give us not A, not B, plus A, B, C bar. But now we can't distribute. We can't factor anything because there's no common factors between that sum. Everything is opposite. Now, so that's going to give us so we're going to need a more complicated circuit to do this guy. So let's make that circuit too. What the heck? Okay, so that's what I was intending to do. Let's go get my logic page. And here we have that. By the way, let's copy that into the notes while I'm here. So I'll copy this guy into the notes. Okay, so we'll put it right over here. Good. Now, so the next guy, oops, oh here, create a new circuit. So, okay, so first of all, we'll name this guy B complement A complement plus AC. Might as well name him, and now we'll create a new circuit. So I'll go here, add a circuit, and we'll call this one A complement B complement plus A, B, C complement. And I'm going to copy the circuit's name and put it in at the beginning over here. Oh, I can't do that. Well, you can just read it. A complement, B complement, plus AB, C complement. Okay, notice the complement. Okay, the order of operation is complement binds tightest, followed by and, followed by or. So this is A and B and C complement. This is A, these two get ANDed, and then the whole thing gets ORed together. So, what I'm going to do is create my A. This time I'm going to need A input, and I'll create a B input, and I'll create a C input, and the C, we only have a C complement. It only shows up towards the end, so let's just just feed in C right into the complement. Okay, so that'll give us C complement coming out of here. And I'll label that guy right here. C complement. Okay, so now I have A complement and B complement, and I'm going to have A and B as well. So I need both of those lines. Okay, so first of all, let's do the A and B is going to go with the C complement. So let's put that down here. This guy, and we'll get the wire for A right here, and we'll put in the wire for B B that way, okay, right into here, and this, so this guy is going to be called, this is AB, and now we'll connect those two all together in an and that'll handle the right part of the equation. So in some ways this is simpler, in some ways not so simple. So we'll go boom. I'll go. And so this guy, we'll label that. Once again, it makes it a lot easier to keep track of what's going on. A, B, C, complement. Now I need A, not A. Need to make, so I've made this side, now I need to make this side. So, I'm going to need not A. I'll hook it to A. And we'll label this guy A complement. And then I need not B. So I need to grab first the B wire. Well, let's grab a knot. Right here, line it up. And we'll wire that to the B. And we'll run that wire out. And that wire is going to be labeled B complement. And stop that. Back to here. And now to make A complement B complement, we AND those two together. So once you have the logic, once you figure out what you want to do with the logic, it's pretty straightforward. And this wire is going to be A complement, B complement. So now I've got my two wires, they're plus, which is OR, this cute little guy. And I'm going to that, and this guy is going to connect to my output. Which is right now unconnected. It shows a little blue thing to show it's unconnected, but we can fix that quite easily. And so 0, 0, 0 is 1, and if we check the truth table for this guy, we see we get 1, 1, all zeros, 1, 0. 4 zeros, 1 0. That's exactly the truth table I was looking for. And so we just put that guy into the notes. Oops, that's not what I want to do. Try it again. Let's start up here. And let's put that guy in the notes. That's better. Now, and we can see, put that down over here. Hello. Now, you don't have, now I don't care if you get the absolute minimum number of gates, but now we're ready to start talking about Project 2. So, we'll switch to your class and the thing. And I want to talk to you for a minute about Project 2. Project 2, you're going to be using the logic gates that we discussed, that's in the book, to build a Logisim single circuit file, which is going to have several circuits, right? One of them is going to read 4-bit and output 1. If the 4 bits are a number from 0 to 9, that is a digit, and 0 otherwise. So that'll be one circuit. One circuit. Another circuit will be reads a 4-bit digit and outputs 1 if they are one of your, if the digit is one of your n numbers, and 0 otherwise. The third run is going to read 4 bits. These will be the outputs of this guy, and returns how many of them are true. So it's going to generate 3 bits to represent 0 through 4. So if none of them are true, it'll be a 0. If 1, it's 1. It'll be 0, 0, 1. If it's 2, it'll be 0, 1, 0. If it's 3, it'll be 0, 1, 1. If it's 4, it'll be 1, 0, 0. And then you want to put the previous to take 4 hexadecimal digits. That's these are the 4 digits that's going to read, returns the number of matches to your n number. If any of the 4 digits are not decimal digits, that is 0 through 9, it's going to return, instead of returning the number that match, it'll return 3 ones, that is 7, to indicate illegitimate input. So you have 16 input bits, 4 4-bit digits, and 3 output bits. And so that's what we're going to do using the technology you just saw. So I think I'll